Hi, my name is Jim, and today's topic is polyphase power delivery systems. And what we're going to start out with is what isn't polyphase, and that's typically the feeds coming into a residence. And there's a pole-mounted transformer somewhere in front of your house or very close to your house that is connected to a portion of a three-phase power delivery system. But coming off the primary here, we're only looking at one phase. And on the secondary of this transformer, and many times these will have pipes sticking out because they're filled with oil to help keep them cool, is we have a center tapped secondary, and there's a ground on the pole for the center tap, and this is called a neutral, and this is a supporting strand that goes to your house. And wrapped around it are two 120 volt feeds, and each of these are 180 degrees out of phase with respect to each other. So what that gives us in our house is the ability to use 120 volts or 120 volts, or for some appliances 240 volts. An example of that would be, say, an electric water tank. I have a well that runs on 240 volts, and stoves, things like that. But this is not considered polyphase. It's more or less single phase, just 180 degrees out of phase. Polyphase has a different definition because when you're talking about polyphase, especially with regard to motors, the output power is constant, whereas with this system, whether you're 120 or 240, there's going to be pulses that associate with the current flow and the power. So motors don't run as smoothly on single phase as they do on polyphase. So single phase is not as efficient, and the power fluctuates, and what that really concerns is motor vibration. There we go. Got some polyphase paper here, I guess. So in the beginning, this is all started out by Tesla. He developed a polyphase alternator, and the phases were 90 degrees shifted. And if we take a look at his original generation, is we would have two resistors, we'll say, and one would be fed by voltage source V2 in red, and the other by voltage source V1 in black. And for a constant load system, if we were to figure out the power by adding up V1 squared over R plus V2 squared over R, and note that R is constant here, and we would refer to that as a balanced load, is that the power dissipation would end up being constant. It would not fluctuate as would single phase. So what would be implied here is the wiring of V1 and V2, if we're connecting it to a motor, would determine the direction of the magnetic field rotation, and that's being the stator windings, the stationary windings, while the rotor winding would follow the rotating magnetic field. And the direction we connect these two relative to ground says whether the field's rotating in this direction or that direction. So later, Tesla improved the design by adding in a third phase, and they are separated by 120 degrees, and I've kind of sketched this out a little bit. And here would be the phasers for it. V1 is the reference phaser in this example, and these are usually referred to as VA, B, and C, but I'm just using the voltage as a reference. 120 degrees apart. And what we would see if we were to look at these kind of as independent sources, now they're really one generator with multiple windings on them, is the power dissipation in these three resistors would also be constant if we were to add them up. So we get the same advantage with three-phase as we did with Tesla's two-phase, except this is a better system to use, and this is a universal standard for power delivery in the United States. Now, the reason in power distribution that we have high tension lines, and you might notice that there will be multiples of 3 on a high tension line, is if we take this simple example here, and this is not in detail, it's just to prove a point. And we're starting out with 120 volts here, and we're getting over here at about 120. It's going to be a little bit less. And what we have is 2 amperes flowing in the circuit, and what we're going to say is that the transmission line from here to there, down the block we'll say, is 1 ohm going out and 1 ohm going back, and we're going to allow 2 amperes to flow. So if we do a little bit of math on this, is what we see is the power line loss is 8 watts. Now that 8 watts is what's being lost by the electric company, and would ultimately be made up by our bills being higher. Further, the voltage drop would reduce this to less than 120 volts, which wouldn't necessarily be good for us. But if that voltage is stepped up to 1200 volts, and the current would then drop to 0.2 amps, and do notice that the same amount of power is being dissipated here, but the power loss, P equals I squared R, when we reduce this, now is 80 milliwatts. So there's a tremendous savings in power line losses if you step the voltage up, because you step the current down, and the power loss in the transmission line is equal to the square of the current. So in 3-phase systems, you can get up to, highest I've ever heard of was 300 kilovolts. I used to run in the early morning and pass under lines like this, and on misty days I could hear it hissing. I ran a little faster then. It's kind of scary, that kind of voltage. So if we step up the voltage, that allows us to use a smaller size of copper wire, and copper is expensive, and reducing the size of it would be kind of a cost savings technique. So if we now look at a 3-phase source, what we're going to see is 3 generators, and remember that these are really in one machine. They're wound together, and we're going to start out with VAN, and N here is the neutral. We'll draw them right there. And all 3 of these reference voltage are with regard to the neutral, which would be typically grounded. And what we can say, if we take a walk around the loop, so to speak, keeping in mind that these are 120 degrees out of phase, is that the sum of the voltage adds up to 0 volts. So what we can say from that is that the absolute value of VA to neutral equals the absolute value of B to neutral equals the absolute value of C to neutral. And the absolute value simply means that we're not including the angle in that. So, in a 4-wire system, what we would have would be the 3 phases and the neutral. If also the load is severely imbalanced, that means that the load between VA and neutral, and VB and neutral, and VC and neutral is very, very much different. That's not a good thing, because the neutral current can actually exceed the phase current. And in recent publications by the NEC, they're suggesting to oversize the neutral wire. And there's another issue in there that's referred to as triplets. Now, what we learned in power supplies is that if we have a half-wave rectifier, it's going to draw like that, and this will be the circuit here, a little diode, a filter cap, and a resistor, is that the filter cap would charge up and then discharge through the load R, and then charge up again, and the only time the current is flowing in this circuit is right here. Now, these half-wave and basically bridge supplies are all over the place in Walmarts, and Walwarts, wall supplies. And what that would tend to do is it would take the power line frequency, 60 hertz, hitting 170 volts peak, and since this is conducting at the very, very peak, tend to round this off a little bit. Now, what that's doing is introducing odd-order harmonic distortion, and that's not a good thing. So, if we were to look at this, say in the frequency domain, where this would be F, and this would be the voltage V, what we would see would be one spectral spike at 60 hertz equaling 120 volts RMS. Now, if we start to round the top a bit, is what we do is we generate a third harmonic, which is a sine wave 3 times the frequency, and a fifth harmonic, and a seventh, and a ninth, and so forth. Now, what a triplet is about is the third harmonic in multiples of 3 in these loops add together. They're series 8ing. And that produces currents which basically flow inside the plant, reducing the transformer, the amount of ability of the core to not saturate, and I²R losses and so forth. So modern power supplies, instead of using this technique, have L's and C's in front of them such that the current would flow through 360 degrees of the input waveform to reduce these triplins. So triplins plus severe imbalances can cause a very, very high neutral current, and the system is totally balanced. The neutral current will be equal to 0. Okay, we have two sequences here. In ABC is called a positive sequence, and here I've sketched the order of that. And in resistive loads, this doesn't mean a whole lot. The transformer outside of our homes is connected to one of these loads, and we really don't care. But if we're connecting machinery to this, it's very important that we get it right. A three-phase motor running backward in certain equipment can do a lot of damage. So the reverse of this would be an ACB, and that's called a negative phase sequence. So if we're dealing with a rotating machine again, we want to get that right. So a little bit more on this in a minute. We'll move on here. We have two circuit topologies in three-phase, and one is called a Y, and this is called the phase voltage across these, and then the line voltage would be from A to B, A to C, and B to C. So we have phase and line voltages in Y configurations, usually referred to as 4-wire. And in delta configurations, as you can see here, the topology is a little bit different. We don't have a ground reference, but this is kind of subject to problems if we have imbalance, because we get mesh currents flowing in the loop there, which is not a good thing. So if we look at this here, what we can say is that the phase current is the same as the line current, which we would expect, because current flowing through the phase is also going to be flowing through the line. And the phase voltage and the line voltage are different, obviously. This is going to be some voltage, and if we go across this, we're going to have a contribution from a source down here. Now, I've drawn these as resistors. You can, in your mind's eye, pretend they're windings in an alternator. So in a delta system, the line and phase voltages are exactly the same. However, the phase currents are going to be different. So what we want to do is look at this a little bit and explore these two different topologies, which are very commonly used in three-phase. So generators usually produce a Y configuration, alternators rather, shouldn't have said generators. Now, suppose that you're working in a factory, say with machining equipment, and the direction of rotation is very important. If you connect it backward, it's possible to do a lot of damage. So you can buy a polarity tester here, and this is a 3-phase tester. I think the price on this was $17. And basically you have 3 wires coming in, and you pick one of them and call it reference. And then by testing with this, it'll tell you, there's little arrows here, you can't see them, what the phase relationships are, whether it's ABC or ACB. So you can connect this correctly to your equipment. Now whenever you're dealing with 3-phase, it's dangerous because there's no such thing as low voltage 3-phase. In high voltage systems, what you have to be very careful of is arc flash. Now I used to work with AT&T, currently AT&T, and on the 7th floor they have a power plant to feed all of the fiber optic cables going through Cleveland and around Cleveland. And a contractor was working, and this was fed by 483 phase and charged batteries. One cell, and this lead acid batteries, is about as high as this, and they're in series to add up to 48 volts. So he looked in the back and he saw that one of the circuit breakers, he'd been working on it and had it de-energized, had a little flap that was holding it in place, and it wasn't completely turned. So he took a long-handled screwdriver and went back and tried to twist it in place and got between 1 phase and ground. Well, that immediately blew up the circuit breakers. That's kind of a major alarm. There's 22 floors in the building, and the beep codes were saying big problems on this floor, and all the managers are required to go investigate immediately when you have a major alarm. So when I got there, this technician, he was sitting down with his hands covering his eyes, and it took him about 10-15 minutes to regain his sight. The explosion must have been terrible. The screwdriver was gone, at least the metal part of it, and he's very lucky that the ejecta did not get in his eyes. So when you're dealing with any kind of power like this, arc flash is the second hottest thing on the planet next to a nuclear explosion. Be very, very careful. Always disconnect the power. It's called lockout tagout. Tagging means that you put a note on it that it's shut off. So somebody else doesn't come along and say, oh, no wonder the machine isn't running, while you're working on it and flips it on. So why source, load, and phase voltages? And there we see the relationship that we saw before, and we're dealing with 120 volts in this example here. And what we're going to be looking at is the voltage difference between VA to neutral and VC to neutral. And what we can see is, if we want to see what this is equal to, is VCA really, stay here, is equal to VAN minus VCN. So this is just the usual difference in voltage that we're used to. And looking at this here, as we see, we have 120 degrees phase angle and 60 degrees on the other side, because 180 degrees across a straight angle. And if we go to analyze this, we're going to take a look at the real component of this, and this is going to be the cosine of the side adjacent over the hypotenuse. And as indicated, this is going to be negative. So what we're looking at here is this angle first. Side adjacent, hypotenuse, and what we can see from this here is we're going to have a negative real component and a positive imaginary component. So it's kind of important to note here when we talk about this stuff, as we're referring to right angles, and 120 degrees doesn't work well with a right angle, but in quadrant 2 it works quite well. So we have to be careful sometimes, especially with tangents, of what we're looking at. Just don't punch it into a calculator and expect it to be the right answer. In sine and cosines it is, and in tangents, as we'll see later, it's quite different. So if you want to compute this by hand, you must be very careful about this, that you don't make an error in dealing with stuff which is in different quadrants. So let's take a look at V-line here. And what I'm going to do here is take a look at VAN minus VBN right here. And I want to find out what the voltage is between the lines. I know what the phase voltage is because I set it to 120 volts, which is reasonable. But across these, what is it going to be? So we'll start out in our first phase here. V sub AN is 120 volts plus J0. It's lying on the real axis. And then if we take a look at this guy, we're going to subtract him. We see that that also is 120 volts at the cosine of a negative 120 degrees. Plus J120, and that's supposed to be sine of a negative 120 degrees also. So when we compute this and kind of write it together, we have 120 volts plus J0 plus 60 volts plus J104. And combining like terms on this gives us 180 plus J104, and then converting that into polar form is what we find is we get 208 volts at plus 30 degrees. So what we would get from this guy and this guy would be 208 with 30 degrees in between here. Now notice that this isn't intuitive, and the reason it isn't is it's hard, at least for me, to picture how this here negative 120 degrees is really going to add to this. You know, I have to do it mathematically to figure it out. I can't see it in my mind and just say that's what it's going to be. A lot of appliances are built to run between 208 and 240 volts. So some places, like the church I attend, has 208 coming in it, and that's used to for the French fryers and fish fryers or whatever else that they have in the kitchen. It used to be 240, and the problem is that the wiring in the church was good, but the line coming in was smoking. So it was upgraded to three-phase. 208's coming in, and all that means is it takes a little bit longer to heat up, say, the grease in a French fryer, but as long as it can keep up, it'll work just fine. So the industry kind of adapts to that to allow the use of three-phase or 240 volts if you're running a conventional single-phase into a dwelling or a business. So if we look at this, it's 208 and 120, and we're going to say that the phase voltages are relatively constant, and they are. And the relationship between these here, if we take 208 and divide it by 140, and I'm just using the absolute value symbols here to avoid the angles, is we see that this comes out to 1.733, and that is the square root of 3. So the square root of 3 plays into this very much all the time. And if we wanted to find out what the line voltage is, and we knew the phase voltage, you know this, and we want to find this, it's just the square root of 3 times it. So in this case we already know it's 208, but you know, maybe something different. And likewise, if we knew what the line voltage would be, 208, and this is what that would look like with these three-phase voltages, this would be at 30 degrees, 180, and this would be 150, is that we would simply take our V line and divide it by the square root of 3. So the square root of 3 plays into this very, very nicely. So that'll do it for part 1, and then we'll continue with taking a look at how we're going to handle currents in a delta load. So yeah, thanks for watching, and we'll see you shortly. Hi, my name is Jim, and this is part 2 of the three-phase discussion. And here we have a delta load balanced, and what our purpose here is to find the currents that are flowing. Our line voltages coming in this case, are 120 volts. And what it did is set up an equation here with mesh currents flowing in a circle. And what we can see is that I line plus I1 is going to be equal to I2, and that'll be the phase current. So to find I2 first is we'll just take the voltage at node A and subtract from it the voltage at node B, and then divide it by the resistance R, which is identical for all three phases, all three branches. Now I could make R equal to 1 ohm, and that would basically drop R out of all the equations, which would make things a little bit simpler, but I've elected to leave it in. So this is what we're subtracting here in polar form, so we'll break that down into rectangular form. I2 here is going to be 120 plus J0, that's this guy, minus our 120 and negative 120 degrees in rectangular form would be a negative 60 minus J104. Combining like terms gives us 180 plus J104 divided by the resistance again, because it is a current, which comes out to 208 plus 30 degrees divided by R. So remember that this is a current, and this 208, even though it is a voltage, is going to be divided by R. So that may be a little bit strange, because you'd be thinking about the 208 that we had in the Y circuit when our phase voltages were 120 volts. Next we'll find I1, and I1 is going to be node C minus node A, so this will be 120 at 120 degrees minus 120 at 0 degrees divided by R. And breaking that down in a rectangular form, we get negative 60 plus J104 volts minus VA here, which is 120 plus J0. Combining like terms gives us negative 180 plus J104 divided by R. So we got all we need to do is to find I line now is just to subtract these two currents, and we'll be all set. The reason we're subtracting them is because we started out with I2 equal to I line plus I1. So if we move the I1 over to this side, we have I line would be equal to I2 minus I1. So doing that in rectangular form, we have 180 plus J104 minus the quantity of this guy. Combining like terms gives us a real 360, and the imaginary terms cancel to J0 divided by R. And then what we'll do is we'll take a look at the ratio of the line current to the phase current and see if we can maybe come up with some common term which is easy to use. So taking I phase over I line, and we can kind of see that the phase current is going to be higher than the line current, because in actuality there's going to be a component of each flowing in the line. Is we see that the ratio ends up being 360 divided by 208, which is 1.73, and that gives us the square root of 3. So what we can conclude from that in a balanced delta load is that the phase current is going to be the square root of 3 times the line current, or the phase current is going to be the line current divided by the square root of 3. Okay. One more little situation here, and this is a 4-wire Y load. What happens if the neutral opens and it's a non-balanced load, like the electric company's feeds don't expect the loads to be perfectly balanced. So I've drawn it like this. 80 ohms is one of the loads on node A to neutral, 100 ohms and 60 ohms, and then we have an open in the neutral wire, which I think I mentioned before is required by code to be of heavier gauge than the phase wires. And the question is what is VN? What is the neutral voltage over here at the load? So drawing in a more conventional form would look like this, and I'm going to use superposition to solve this. And when you do that, you make one source active, and then you replace the other sources by their internal impedance, which, since these are voltage sources, that would be 0 ohms. So you end up with 3 parts of this that you then add together and get the total answer. So if we do that, here will be part 1, and I'm going to let VA be active. And VA is defined as 120 at 0 degrees. And this is going to be the one with the 80 ohms in it. Flip that real quick. And then since these two we're going to treat as short circuits, what we're going to have is effectively 160 ohms in parallel. So when we go through analyzing this, just remember one is active and the other two are replaced by their internal impedance, which is 0 ohms. 100 in parallel with 60. And that gives us 37.5 ohms. So voltage divider here, we're starting out V neutral, node A is 120, and what we want is the voltage drop across this, because this is going to be our neutral line here. And here's our 80 plus 37.5, which is the total resistance of the circuit as we would expect in voltage divider. And this V node A acting by itself produces 38.3 volts at 0 degrees. So when a neutral voltage moves around, that can be very, very bad for appliances that are connected between the phases and neutral. Next, part 2 will let VB be active, and now VA and VC will be replaced by short circuits as before. And then we'll have 80 in parallel with 60, which will give us 34.3 ohms. And this is those two sources acting as shorts. And then we have the 100 ohm resistor in voltage B leg. And what we want to do is find the neutral voltage relative to ground. Same thing, voltage divider, and that'll produce 30.6 volts at a negative 120 degrees. So that would be the contribution of VB acting by itself without the other sources involved. Part 3, the last part, same deal here. This is going to be 80 in parallel with 100, which is the internal resistance associated with the A and B sources. And we have 60 ohms here, so what we end up with here is 44.4 ohms. That's a combination of those two. And using voltage divider, we see that the V neutral with source C active comes out to be 51 volts at plus 120 degrees. Now all we have to do is add these together and we're finished. So I've rewritten everything here in polar form, and if I want to add these together I need to break them down into rectangular form. So we'll start out with the first one, and this will be VA here, so he's 38.3 plus J0, and then I'm going to add to that the contributions of the second source, negative 15.3 real, negative J 26.5 imaginary, and then finally add in the third source, negative 25.5 plus J 44.1 volts. And I'm adding these vertically here, so I'm less likely to make a mistake. And the reals come out to be negative 2.2 volts, and the imaginary comes out to be plus 17 plus J 17.6 volts. So if we combine these by taking the square root of the sum of the squares, we end up in polar form with 17.8 volts inverse tangent of our imaginary 17.6 over negative 2.2, and then working that with a calculator with the inverse tangent would give us negative 81.9 volts. Now that kind of implies that we're in the third quadrant, and we have to be very careful when you do this. So what I've done is I've sketched this out in rectangular form here, and what I see is that the real voltage here is on the negative real axis and the imaginary voltage is on the plus J axis, and this 89.1 degree angle actually is between the negative real and the phasor. So by sketching it out, that kind of tells me a little bit more about what's going on over here. And you have to remember that the tangent is equal to the side opposite the angle, which would be this guy divided by the side adjacent, which is this. So that's saying in the second quadrant, and if I want to get that angle relative to the positive real axis, I have to subtract this angle from 180 degrees, and that in fact gives me the correct angle of 98.1 degrees. So the neutral here would be 17.8 at 98.1 degrees, and that would be relative to the real axis. Now that means that some phases are going to have higher than 120 volts and some phases lower. And I've actually seen this happen. At football games, baseball games, and basketball games, they bring in a semi-truck, and in it is a lot of video switching equipment. All the cameras feed the truck, the announcer feeds the truck, the slow motion equipment's in the truck, and there are producers in the truck. And then they combine everything in accord to what they want to do, and this is handed off to a company like AT&T to get it across country. Well, they lost the neutral, and because of things like this, some of the voltages in the van went up to 140 volts or whatever, others went down to 88 volts, and the high voltages burned out a lot of equipment. And that's not really a nice thing to have happen before kickoff. So they finally got it to the point where the van was running, and they called us. It was Ameritech at the time, now AT&T, and they were complaining about 60 hertz interference in the video. And that typically happens when the grounds are a little bit different. And what had occurred is that we have a piece of equipment that stops grounds from interfering with the video, and the loss of that neutral destroyed that piece of equipment. It cost $150 at the time. Now the dangerous thing about that is if the shell of the truck was connected to neutral, it could have been hot. Now 17 volts may not seem like a lot, but it could have been a lot worse. This is only an example of what I made up. So that's kind of our overview on three-phase. It's a very, very common power distribution. You see it a lot in industry, a lot in factories. And have to be careful of it, and just remember the square root of 3 for balanced loads and balanced sources. So thank you for watching.